Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Welcome back. We're in AP Physics 1, still in Unit 3. We're doing work, energy, power. This is the last topic of this unit, and power is what we're going to do today. So we're just going to power through this video and get started. Pun intended. All right, I'm going to come over here. We have power. What is it? We got to define it first. It's the rate at which work is done, or the rate at which energy is transferred. Okay, or transferred or transformed, actually, either. So it's a rate. It's going to be divided by time. But let's just jump in right here on this symbol. What is the symbol? This symbol is a capital P. Now the unit I'm going to write way over here because there's going to be several of them. Sometimes that's a question on a test. Which one of these is not a unit for power? Because it's going to come in many forms here. We're going to show you. They're all equal, but there's different ways to say it. The first one is a watt. All right, James Watt was a Scottish inventor. He worked on some developments on the steam engine, and the honorary unit then was given to him for power. And I like to tell my students, J.J. Watt has lots of power, so that'll help you remember what that unit is for power, that honorary unit. Because now we have a Newton for force, we have a joule for energy and work, and now we have a watt for power. All right. Let's just jump in here now with equation. Okay, the basic equation for power is that power equals work divided by time, or your change in time. Okay, now that's that rate at which work is done. Work divided by time, that's a rate. So work is measured in joules and time is in seconds. So another unit is a joule per second. And these all come out to be the same, actually, when you're talking about SI units, and I'll show you momentarily. Now, the other thing that work divided by time, and you'll often see it as W over delta T, like that, is really the equation there, equals power. All right, is that work is that parallel force, parallel to displacement, times your displacement, divided by time. Okay, that's another equation that you can use for power. If they give you work and they say this whatever this force was did 10 joules of work in 1 second, then it would be 10 divided by 1 and you would have 10 watts. All right, but if they gave you a force and a displacement, you could multiply those, making sure you're getting that parallel force to displacement, and divide by time, and you would also get power. All right, but now look at this. Oh, and by the way, force is in newtons. Displacement is measured in meters. So a newton times a meter over a second is also another unit that means the same thing as joule over second. It means the same thing as watt. Now, look at this. If I put this, let me put this in another form here. Your parallel force times displacement over that delta T. Look at this displacement divided by your time. That should look familiar from the first unit. If we do delta X or delta T, that should look, that change in position or your displacement, I'm saying, that's change in position, meaning displacement, equals, it should, if you guys remember, it should equal velocity from the first unit. So look at this. If I put in velocity for this, then you get that power is also equal to force times the velocity. And so we have really several equations we could use for power. If they give us work divided by time, and they already give us work, then we're good with that equation. If they give us force and displacement and time, then you're going to be using that one. If they give you force and velocity, then look at this. You're looking at this formula. So again, you're going to let that problem guide you, and you're going to see what you have been given to know what variables you have for which equation that you're going to pick. All right. Now, the other thing is to say here, to look at the SI units, we know that a Newton is a kilogram times a meter over a second squared. And you're like, why do we know that again? Because a Newton is mass times acceleration. So mass is kilogram, acceleration is a meter per second squared. All right, but remember, that's just in Newton. That's just the Newton. That's in. We're multiplying it times another meter, and we're dividing it by another second for power. So that is a kilogram meter squared over a second cubed. So what that actually equals, I'm going to rewrite that, so hopefully you see what I did there. I took a Newton, I multiplied it by another meter and divided by a second, and I got, I'm going to clean that up now, a kilogram times a meter squared divided by a second cubed. All right, and that is the SI unit for a watt. And that's actually exactly what this is, and that's exactly what a joule per second is, and that's what the watt means. It means a kilogram times a meter squared divided by a second cubed. All right, perfect. Now that we understand the units, we know the formulas, we're going to look at some concepts because these are really important. All right, I'm going to use my dog today. We've been using my colleague Beth's cat. We're going to use Annie, my dog. She's a 10-year-old lab that we love. But my concepts are here. I'm going to use those. The first one is that Oakley, I'm going to use Oakley. Oakley is my daughter's dog who is very active and loves to run in the woods around here. But Oakley does twice the work. Maybe she's running and she's powering through the woods, but she does twice the work in half the time. That Annie, our dog, that Annie does. Okay, maybe they're running upstairs, maybe they're running through the woods, but Oakley's doing twice the work in half the time as Annie. So how you're going to do this, here's going to be power for Annie, it's just going to be work divided by time. But power for Oakley, and by the way, this is a very true statement, Annie is 10 years old and just likes to lay around. She actually has a little problem with work and energy because she doesn't like to do any work to have any energy. But anyway, so twice the work, we're just going to put that 2 in for work and we're going to put that half in for time. I used to have an algebra teacher, shout out to them, in junior high that said when you've got a fraction on the bottom, on the denominator, flip it. Flip it. They kept saying flip it. So that equals actually 4 times work over T. Or 4 times as much as what Annie did is Oakley's power output. So her output would be 4 times as much. All right, so pretty easy concept there. Just if whatever number they give you, fill it into the equation, work it out, and see what the difference. This was Annie's power output, and this was Oakley's, so it was 4 times as much. Now, here comes another question. I'm going to erase this. The other question is, hey, we've got Oakley and Annie going up a mountain. So we've got our little mountain here that's around where we live, and we all are starting. Annie and Oakley are both starting at the base of the mountain, and they're both going to finish here, and this is their start. All right, Oakley, because she is the dog she is, she's going to run straight up this thing. Whereas Annie is going to be slowly winding up the mountain and on a path, probably. All right, where Oakley's charging up on her own, making her own path. All right, so the question is, if compare their work and compare their power. Knowing that when Oakley charges up this mountain, she is doing it in less time. So Oakley is going to arrive way earlier. Oakley will arrive way earlier than Annie. Okay, so we need to compare their power and their work. Okay, first of all, they both do the same amount of work. And how do I know that? Because the start and finish, remember we said, hey, that force due to gravity is a conservative force, and that work is equal to that change in energy, change in kinetic energy, but if you have a conservative force, you can also use it and apply it here. And that change in energy would have been potential energy. They both started on the ground and they end up at the top at rest, so that's going to be that mgh final minus mgh initial. And I should have also told you that Oakley and Annie have the same mass. So mass for Oakley is going to equal mass for Annie. All right, so their work is exactly the same. Same mass, same G, 9.81, same final height at the top, and same initial height. So their work is equal. However, Annie takes way longer getting to the top. Oakley speeds to the top and Oakley beats her there. So if I did power equals work divided by time, they both have equal work, but Oakley's time is less. It took her less time to get to the top. Well, when you decrease a denominator, your overall number is going to increase as long as this numerator stays the same. So in other words, let's say they did 4 joules of work in 4 seconds. Annie did. Okay, well, let's say that Oakley then did the same 4 joules of work, but this would be Annie, power for Annie, and then power for Oakley, just making up numbers, she did it in 1 second. Well, Oakley's power is going to be greater. Hers is going to be 4 watts, whereas Annie's is going to be 1 watt. So when Oakley did it in less time, it reduced that denominator and made the overall power increase. So Oakley had a higher power output, even though they both did equal work. All right, that is our quick lesson on power. Hopefully you understand what power is now from a physics definition, and you know some different formulas that we have and all of the units for power and a couple of concepts. Thank you for watching. If you liked this, be sure and like it and subscribe if you want to see our next videos coming out in the next Unit 4. And thank you for watching, and happy physicsing.